All right, so now we're going to do the same theorem again, but with a different proof. Okay, so again, we're trying to prove that if V is finite dimensional and a complex vector space, then given an operator on it, V has a basis with respect to which the matrix of the operator is upper triangular. So the last proof worked by restriction, the idea of restricting to a subspace. We looked at the range of T minus lambda I. This one works by modding out, which is another way to study a smaller subspace, or the action of an operator on a smaller subspace. So we'll look at a quotient map. And so again, we're going to go by induction on the dimension of the vector space. And also, again, the result is obvious for n equal to 1. So we're going to make our inductive hypothesis, which is that we assume the result holds for any space of dimension n minus 1. So the other one was what was called a strong induction. We assume that it works for everything of smaller size. This is what's called a weak induction, where we just assume that it worked for the one on the previous step. Minor technicality. And completely unimportant. Okay, so let's let V1 be an eigenvector. Wow. An eigenvector of T. And this is okay because, again, this follows from the existence of eigenvalues theorem that was done in 521. All right, so we're legit in doing that. Then if we look at the span of V1, this is a one-dimensional invariant subspace of V. And it's, well, invariant under T. So I don't know if you want to call it subspace of V or an invariant subspace for T, whatever. You know what I mean? Okay, so here's the idea, right? So we've got, let me switch to green ink for thinking. Here, we'll do thoughts in green. So V looks like some one-dimensional subspace. U directs some other junk, right? And what you'd like to do is say, okay, so T is an operator on V, so it maps V back to itself, right? And we know that U is invariant, so it maps it back to itself as well. And so then you'd like to say, okay, well then it must map W to itself. Wait, no, that's not necessarily true. It's perfectly possible to have T mapping things from W into U. That might happen. Okay, so W is not invariant under T. But here's a thought, right? So we'll stick in green. W is isomorphic to V mod U. So if we pass to the quotient map, then what happens is we do get something that's going to be taking V mod U back to itself. And the reason why is because any of those vectors that perhaps T was taking from W into U, well, under the quotient map, U is 0. And since 0 is always contained in every vector space, 0 is definitely contained in V mod U. And so somehow it elegantly circumvents that whole problem of things escaping to another space. In other words, when you do modding out by something, you're saying, I only care about elements up to a subspace. I don't really care about like what happens in that last subspace. And so when we mod out by U here, we are formalizing the idea that we don't care if stuff is like jumping out of W. We'll just fix it, and then the resulting thing will be invariant. So it's a very slick idea. Okay, so getting back to the black ink, let's see. So now the dimension of V mod U is going to be n minus 1 by 389. And so that means our inductive hypothesis applies. To this operator T mod U, which is an operator on V mod U. And so, in other words, that means that V mod U has a basis, and we'll call it V2 plus U up through Vn plus U, because that's what elements of the space look like. So that's what also elements of the basis would look like. For which the matrix of T mod U is upper triangular. Okay. Whence? I always love a good whence. T mod U, if we apply that to some element of this space, so Vj, or sorry, one of those basis elements, Vj plus U, then this is going to be in the span of the foregoing critters. By our invariance of triangular basis lemma or proposition. And so then this is true if and only if. So let's unpack what I just wrote in the previous line. So if you remember how the quotient map works, T mod U applied to that thing is going to be TVJ plus U. And then let's see, for this to be in the span, this means that it looks like A2 times the first one plus da 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 plus AJ times the last one. So we've got some linear combination like this. And if you recall how algebra works in the quotient space, this means that we've got A2 V2 plus da 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 AJ VJ plus U. Okay, so that's just using arithmetic in the quotient space. Then TVJ plus U looks like that linear combination plus U if and only if TVJ is in the span of V2 to VJ. And actually, now that we're out of the quotient space, this uses all of them. Whoops, up to up to n. There we go. Okay, so then using our invariance of triangular basis lemma again, the matrix of T here is upper triangular. For this basis V1 up to Vn. And we are done. And you'll notice this proof is actually a bit shorter fair bit shorter than the other one. Slick.